Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's webinar, Enabling Machines to See with Efficient Embedded Vision Processors, brought to you by Tech Online, Synopsys, and broadcast by UBM. I'm Chris Keach, and I'll be your moderator today. We have just a few brief announcements before we begin. First, the slides will advance automatically throughout the event. You may also download a copy of the slides by clicking on the green folder icon located at the bottom of your screen. You can also participate in our Q&A session by asking questions at any time during this webinar. Just type your question into the Q&A text area located to the right of the presentation window, and then click the Submit button. Please note that we'll try to get to as many questions as we can at the end of our webinar today, but if we're not able to get to them, someone will get back to you via email. And at this time, we recommend that you disable your computer's pop-up blockers. This will allow the slides to advance automatically throughout the event. And at the end of the webinar, we will ask you to complete our feedback form. Your feedback will provide us with valuable information on how we can improve future events. You can also launch the survey at any time by clicking on the red survey button at the bottom of your console. And if you're experiencing any technical problems, please type your issue into the Q&A text area, and we will be glad to offer one-on-one assistance. And now on to the presentation. Enabling Machines to See with Efficient Embedded Vision Processors. Discussing today's topic is Mike Thompson. Mike is responsible for the definition and marketing of the ARC microprocessor products at Synopsys. Mike has more than 30 years of experience in both the design and support of microprocessors, microcontrollers, IP cores, and the development of embedded applications and tools. He has worked previously for Actel, MIPS, Zilog, Philips Signetics, and AMD. He has a BSEE from Northern Illinois University and an MBA from Santa Clara University. It's with great pleasure that I now turn this special session over to Mike to begin. Mike?
Thank you, Chris. Hello, everybody, and thank you for joining us today for this webinar. Vision is something that we all do all the time. We take it for granted. It's very easy for us. We don't spend a lot of time thinking about how we see. But vision is actually extremely complex, and it's been quite a challenge to bring that capability to machines. But we are doing that now, and we're bringing it to embedded SoCs in embedded environments and making it available there, which is a challenge because of the power consumption and space limitations. But the capability is advancing rapidly, and vision is something that will change our world over the next few years. So today, I'm going to talk to you a little bit about the embedded vision markets, then I'll talk about a new vision processor that we just announced, the tools that we have to support that vision processor, and then I'll talk a little bit about post-integration, which is critical on SoCs. So vision's been around for 25 years, maybe even 30 years in university settings on supercomputers, things like that. It's only been in recent years, and I mean really recent years, that we've been able to bring vision capabilities to SoCs. The challenge, as I said, in scaling that down is power consumption and the size of the circuit or the function, because vision requires a tremendous amount of processing power. In fact, just a couple years ago, we couldn't do it because the process technology wouldn't support it. We just couldn't put enough transistors into a small enough space and low enough power. Plus, the processor technology wasn't really there. There's been some significant advances in process technology, processor technology, as well as the algorithms that we use for vision. And this is going to start showing up in cars. Certainly, it's already there. I have a car that can see the lane and steer itself. But surveillance is another area that we're starting to see a lot of growth. Industrial, I think ultimately over time, industry will probably be the biggest user of vision. But you can see the market's growing at a very rapid rate, and it will continue to do so. This chart tops out at 2020. But if you go to 2030, the growth continues to be that staggering. And it's because, again, when we bring vision into machines, we allow machines to experience the environment the way that we do, and it becomes a much more natural interface for them and for us. I mentioned surveillance. This is a very fast-growing area for vision because you always hear like London has X zillion cameras or New York. The problem with having all those cameras is they generate a lot of data, more data than we as people can reasonably look at. And so we're finding ways to process that data in meaningful ways that then can highlight that to a person to do something about it. And so vision is seeing tremendous growth in the surveillance space. Also in automotive. Automotive is probably the area that will come the fastest for us in terms of vision. Already, lots of cameras are being implemented on cars. It's not unusual today to find a car that has 4 or 5 cameras on it. I've talked with some of our automotive customers who are building systems for the future, and they expect as many as 15 cameras to be implemented in cars in as little as 5 years. And this will completely change the way we drive. But this is coming very rapidly. They highlighted front camera on this because that's one of the most interesting areas where vision will be merged with radar and other capabilities to image the road in front of us. But, of course, the benefit of self-driving cars is the reduction in accidents, the safety that it brings, and the leisure that it brings us in terms of time. But this is a great example of what vision will do to our lives. So these are the areas that we target with our vision processors in the market. Of course, mobile applications in it. The jury's still out exactly what vision will be for mobile. I expect it'll be built more around augmented and virtual reality. But ADAS, of course, in car surveillance that I mentioned. Drones is an area which is getting a lot of media play today. And it's growing fast. Virtual reality is an interesting area that is very much in its infancy, and we'll see it develop over the next few years. Gaming is a natural, which we'll see how much. I mean, there's already Kinects and things like that. Cameras, another interesting area. I put a picture of a regular SLR camera here. But one of the more interesting areas is industrial applications for vision, where they can do quality control and hold very, very tight tolerances on things using vision systems. Retail is an area also where your experience going into a store will change dramatically over the next few years as they bring promotions and advertising specifically to you as you move through a store. And, of course, home automation. It's not really clear how vision will play out in homes because a lot of people don't like to have cameras or the thought of having cameras staring at them, but certainly there'll be a lot of application in our homes as well. So let me talk to you about the processors. We announced these a couple weeks ago. This is the DesignWare EV6 family of vision processors. Now, Synopsys has been involved in the vision space for a number of years. We introduced our EV5X family last year. These EV6 processors have about 100 times higher performance than the EV5 family. And that's the magnitude of performance advancement that I expect to see in the vision space over the next few years. This will continue to play out successively, at least an order of magnitude greater performance from generation to generation, to process the tremendous amount of data that is in a video frame or a video stream. Now, the EV6 family is a very highly integrated processor, combining a very advanced signal processing capability, or vector DSP, with a very specialized engine for processing convolution neural network graphs. So the processor brings all that together in a single package, again, small size, low power. Supports streams. Actually, you can use it for VGA if you wanted to. It can be scaled down for that, but it'll support streams up to 4K 60, which is a tremendous amount of data. That's 8 megapixels per frame of data at 60 frames per second. And the processor is completely scalable, configurable by the user, so you can tailor it to your application. Again, if you're doing VGA streams, we don't see too many people wanting to do that anymore, but a couple of years ago, VGA was the norm. Today, the sweet spot seems to be 2 megapixel or 1080p. And I expect that'll move forward to 2K pretty quickly, 4K, and maybe even 8K, certainly 8K in time. But the processor itself is scalable, so you can control the number of vision CPUs. Those are highly configurable. The CNN engine itself can be configured to some degree, so that you can tailor it to your application to give the level of performance that you need, but also limit the power consumption, to control the power consumption in an area. And of course, we have a complete set of tools to support the processor. You can imagine a processor with this level of complexity requires a full set of tools to program. So this is drilling in a little bit deeper. This is the vision CPU. Again, these can be implemented with 1 to 4, depending on which of the EV6 processors you get. The EV61 has 1, the EV62 has 2, the EV64 has 4, and these are configurable. So you could configure it with just the 32-bit scalar core if you wanted to use that just for control and communication. You can also configure the vector DSP, depending on how you want to use that. Now, with 4 of these, you get a very high level of performance that, again, will support 4K video streams with 620 GOPS of processing capability per second, and that's at 800 megahertz. The vector DSP has been designed to be programmed with OpenCLC with full vectorization capability to make it easier to program, but also because we designed it to run OpenCLC, it's also more efficient, so it reduces the number of cycles and the power consumption. That was intentional. And we have full scatter gather capability and predication to keep the performance high, and that's built into the vector DSP. Now, I mentioned the CNN engine on the previous slide. The vector or the vision CPU and the CNN engine operate in parallel, so you get more performance out of the processor overall and becomes more efficient. You can essentially do 2 things at once. Convolution neural networks have been around for a number of years. Neural network technology is getting a lot of media attention recently, not just for vision, for a lot of things. In fact, neural network technology is used to do the character recognition for check clearing. So if you all remember what a check is, I don't write very many anymore. I suspect most of you don't either. But when you do cash a check, it goes into the bank, and the bank uses a program that uses neural network technology to read that check. And they do that because neural network technology is very accurate. It's more accurate than any other algorithms that we have today. And convolution neural networks are a specialized form. It's used primarily for vision applications. It's a deep learning approach that operates in a way that's similar to the way our brain works. And it uses an offline training, which would be done in the case of CNN on a server farm or a GPU farm. They'd take a lot of images of something, say a face. If they're doing face recognition, you take 100,000 images of facial images, scan those in, run an algorithm on that, creates a CNN graph, which is essentially a model of the face, and then that can be programmed into the CNN engine to find faces in video streams. And it does it very accurately. We see accuracies in this F1 scores, which is actually the accurate, or the faces found minus the mispredictions. We see that running in the 85 to 90% range, which is as good as you or I can do. Now, human experts can get up into the low 90% range. And actually, high-end machines today, when they have the high-end bake-offs, do better than human experts. So this technology is moving ahead very quickly. So this is a look at the CNN engine. It's a dedicated CNN engine, so this can be used only for finding objects or scene segmentation or classification of objects. It can't be used to run other algorithms. And we did that on purpose because by making a dedicated engine, we can take advantage of the CNN algorithm, delivering very high levels of performance, much higher than what competitive solutions can offer. But we can do that very efficiently at very good power consumption. In fact, it says that the power efficiency is greater than 1,000 GOPS per watt. It's actually greater than 1,500 GOPS per watt, or that's billions of operations per watt, which is a phenomenal level of power efficiency. Of course, we fully support 4K resolutions. The CNN engine, while it's very efficient, is also fully programmable, so we can run any fixed point CNN graph. And we do that, of course, in real time. It gives us very high image recognition accuracy, full classification capability, and then semantic segmentation, which is the ability to look at a video frame and separate, for example, sky from road, from buildings. And that requires a lot of compute because you have to look at every pixel then in the image and classify it. So it takes a lot of performance, but we can do full semantic segmentation. That's important in applications like drones, for autonomous flight, or cars where you want to separate the road. This is the road, now let's look for the lane markings, kind of thing. And the CNN engine operates in parallel with a Vision CPU, as I said on the previous slide. Again, it gives us good efficiency, but allows us to do multiple things at one time with the processor. So this is a little more on scene segmentation. Again, this is important. Autonomous vehicles, drones, I expect other applications will develop over time. I think augmented reality to some degree will use this, virtual reality as well, depending on how much you're interacting with your environment. At the bottom, there's some statistics on our benchmarking that we did on what's required for just 1080p 30 frames per second. It takes tremendous compute power. You can see on a 16-bit pixel depth, it's 622 megabytes of data that has to be processed per second, which is a lot of information now. If you want to go to 2K or 4K, take that times 2, times 4. It becomes a lot of information that has to be processed in real time. It really requires a dedicated engine to do that. By the way, the weights at the bottom is the coefficients. And one of the advantages or one of the capabilities that we bring by having a dedicated engine is we can build the engine in a way or architect it in a way that allows us to keep the coefficients or the weights to a minimum. And what that does is it also reduces the amount of memory that has to be implemented around the CNN engine or with the CNN engine. And typically, most applications can be implemented with under 500K bytes of memory. Now, another aspect of vision which I mentioned briefly on the previous slide, is the tremendous amount of data that has to be read from a frame buffer somewhere and streamed into the processor and processed, and then something has to be done with it. There has to be some response. So we've developed a very specialized DMA engine that we call a streaming transfer unit that allows us to, in the background, move this data very efficiently from the frame buffer. And that frame buffer may be on chip or it may be off chip. We really don't care, as long as we have enough bandwidth, access to it, get the data in real time. But allows us to move the data very efficiently. It does all the addressing, tracking of the data, brings it into the processor so that the Vision CPU and the CNN engine can focus on the task at hand, and then the STU manages the data in the background. You see some of the transfer rates, 32 gigabytes per second. That's bytes, not bits, per second at 500 megahertz. We expect most of the applications that use this processor will run at about 500 megahertz, although it can be clocked as high as 800 megahertz. So I put this slide in so you'd have a sense of some of the capabilities. So if at low, this configuration high, medium, low is arbitrary. I just put that in there. But in a low configuration, which would be a single Vision CPU, VDSP is vector DSP, but a single Vision CPU core running at 500 megahertz with a CNN engine configured to a very low number of operations per second at 220, could support a single camera at 2 megapixel, 30 frames per second, which again, 2 megapixel is 1080p, so nice capability, relatively low power in the range of 350 milliwatts of power consumption running at that speed. The CNN engine, of course, can do the same performance. At a medium level, now we have two Vision CPUs. Again, the same level of performance with a CNN engine, so it's going to have the same operation capability. Now we can support 30 to 60 frames per second, 1080p. If we go to medium high, or let's go to the high level, I mean, there we can support multiple cameras, single camera 4K resolution, but multiple cameras with 1080p. Keep in mind, 4K is 8 megapixel. So a lot more data being processed. Full scene segmentation now on a 1080p image, which is, again, a lot of data being processed. So let me talk just briefly about the programming tools. So we have a full programming environment. This picture looks a little bit complex, but let me break it down for you. We have an OpenVX runtime, which allows you to build a vision graph. It's convenient because it gives a level of abstraction from the hardware, which is nice for the programmers. They don't have to spend so much time thinking about the hardware. It can spend a lot more time on the vision graph itself. But you build a vision graph with the OpenVX runtime, which is a collection of kernels that can come from a number of different sources. We fully ported the OpenVX kernel library, which is 43 kernels that have been ported and optimized for the EV6X family. We also have full support for the OpenCV library, and we're actively building kernels from the OpenCV library, additional kernels in addition to the OpenVX kernel library. We expect over the next year to have in the range of 75 to 100 of those kernels as well that we'll make available to the processor, the users of the processor. And those kernels can be put together to build a vision graph. Of course, users can write their own kernels, either with C or C++. or with OpenCLC. C or C++ would run on the Scalar core in the Vision CPU. The OpenCLC would be used for the vector DSP that's in the Vision CPU. And then finally, we also, you can get kernels from the CNN primitives. And when with CNN training, graph training is done offline, but then the CNN graph, we have a tool that automatically maps that to the CNN engine, and at the same time it will generate that CNN primitive that you can use with the OpenVX runtime. So it becomes very easy to put together the vision graph from the programmer's perspective, and then program that up to run on the vision processor. Now, let me build this slide here real quick. The nice thing about the OpenVX runtime is that it allows you to direct the kernel to run on a specific resource. So, for instance, the UI kernel there, the light blue on the left, would run on the 32-bit RISC core. The two red ones would run on one of the vector DSPs, in this case on different cores. So, and of course, the darker blue ones would run on the CNN engine specifically. But the resource can be specifically directed by OpenVX inside the kernels to run a specific resource. And that's important because these are sophisticated structures, and the ability to target the resource within the processor is critical from a programmer's perspective so that they can make maximum utilization of the processor itself. One thing that we do support is tiling within the processors. What this is typically, or in previous vision processors, the frame would be brought in its entirety, brought into the processor. You go through the first phase of analysis. There's a number of phases in the analysis of the video frame or a frame from the video stream. There's the pre-processing to do grayscale conversion, image pyramid, any pre-processing, other pre-processing, any image enhancement that has to go on. And then the frame would be interrogated for whatever object or objects are being looked for scene segmentation, if that's what's being done. And then the information passed back. So at a minimum, the frame's going to have to be fully read and saved 2 or 3 times. And that takes a lot of memory and a lot of memory bandwidth, which translates into power consumption. With tiling, what we do is we just take the first 10 rows from the frame and feed that into the processor and start analyzing that, and then pass the results of that to the next stage and on through the processor. And what that does, it allows us to read the frame once, and then more than likely we don't actually ever have to write the frame back, because typically whatever's fed back wouldn't be the full frame, but it would be coordinates or some other information that would be used by another portion of the system. But this becomes very efficient in terms of memory and power or bus bandwidth, because we only read the frame once and we read it through a little bit at a time. So the Metaware Development Toolkit has been developed over the last 25 years, and in recent years has been fully optimized to support the ARC microprocessor capability that Synopsys offers, which we use inside of the Vision processors. This is a very efficient processor, supports C or C++. The toolkit also includes a full debugger, instruction set simulator. It's a nice environment for developing the C or C++ kernels that you're going to run on the Scalar CPU. We also have support for OpenCLC. This is whole function vectorization. Now, the vector DSP is 512 bits wide. Typically, we expect it to be configured as 32 16 by 16 max, although you could configure it as actually 64 16 by 16 max. We do support a dual 16 by 16 capability. But programming each one of those Macs independently is onerous at best. But OpenCLC makes that task very straightforward because one line of code can be used to program the whole vector array. And the lanes, of course, execute on the same program but different data. We have, of course, again, as I said, full support for scatter gather, so the results of any lane or any Mac can be reused by any other Mac, as well as predication. And, so you can process different information as it goes through, but OpenCLC makes the programming very straightforward and easy. Right. We also have a tool that will take the CNN graph that's generated offline and automatically create a number of views of that, one of which is the CNN target binary at the bottom, which would be programmed into the CNN engine to run the CNN engine. It also creates a model, fixed point C code model that can be used for reference, for simulation or other tasks. It also creates the kernel. So you have all the views that you need that generated automatically, so you can easily program the CNN engine and use it in your application. We have full support for FPGA-based development system using the Synopsys HAPS 80 system. This allows you to build, or we actually give you the scripts for the EV6 processor, so you can easily program that in to the FPGA on the HAPS system, and you can actually build your whole system with HAPS if you want, or you can just model the vision processor. But what it does allow you to do is finish and build your software program and debug it well before you have silicon, so that when you get silicon back from fab, you have a program that's been debugged that you can run on it. We also have full support for virtual environments with a virtual development kit, so that you can, if you're modeling your whole system in a virtual environment, you can model it with the Vision CPU and run your programs against the rest of your system. We built the virtual, the VDK with host integration with integrated hosts, so you can see how that's done. In this case, we used an ARC processor, but you can use any processor for your host. We just gave the ARC processor as an example. And we include all the scripts for the use of the VDK in your environment. All right, we also have a number of other capabilities that we make available to you. We have, I mentioned the OpenVX kernels, as well as the porting that we're doing, building additional kernels with OpenCV. We have a couple reference designs that we've done, one for speed sign detection, one for face detection, that we make available to our customers. We give you the full source code for those, again, and those are done with host integration. So you can see how we built the code using the OpenVX runtime, how we built the vision graph, how we access the different resources on the processor using the kernels, how we did the host interface, and built the whole thing. In fact, these reference designs are done in a way that if you wanted to, you could use them as a skeleton program for your own design. We're also working with partners to develop other capabilities image enhancement capabilities, and other vision processing capabilities that would be used in either the pre or post-processing for the different vision applications that would be run on the processor. And then we have a lot of benchmark information that we can make available to you if you're interested on the processor itself. So let me talk briefly about host integration. We expect that in 75 to 80% of the designs that are done with the vision processor, there will be a host processor on the SoC. In many of those applications, there will also be a GPU. And as you know, a GPU could be used for the vision processing, but what we're seeing is a trend to build in a separate vision processor, which sounds a little bit self-serving, but when you think about it, it makes a lot of sense because the GPU, one, while it's capable of doing the vision processing because it has a lot of DSPs, typically a GPU would be used for other things, so there's probably not a lot of spare cycles to do the vision processing, which takes a lot of horsepower. Also, GPUs aren't very efficient in terms of vision processing. They use a lot of power. As I said, they're probably doing something else for the SoC or the application the SoC is being used in. So using a vision processor makes a lot of sense. It's much more efficient in terms of power consumption. It's not large in terms of area. And it can be used to do a broad vision capability. Now, the EV6 family has been designed to be easily integrated with a host processor, and I'll show you a little bit more about that on the next slide. We are very host agnostic. Of course, we'd like you to use an ARC processor because that's what Synopsys licenses, but if you're using an ARM host or Intel or MIPS, it doesn't matter. We give you the same access to the processor. The processor itself connects to an AXI bus. One, so that we have very good transfer rates from the frame buffer, but also so that there's very easy connection to the rest of the SoC to any host. Maybe there's another DSP in the system. We've seen that, or a GPU, as I mentioned. Right. Let me show you just briefly the host integration. And you can see this if you look at the VDK or even the HAP scripts that we have or the reference designs, you'll see the host integration. But there's a number of interrupts that exist that can be used between and sync signals between the vision processor and the host or the rest of the SoC, whatever you're trying to sync with. Also, portions of the memory there at the bottom is actually the memory that's inside of the vision processor, and that memory is configurable by you up to, I think, 8 megabytes. But the host can see portions of that memory, so it's very easy to pass information, communicate with the host. And really, the vision processor has been designed in a way that allows you to decide how much control the host is going to have over it, from pretty much complete control to a totally autonomous operation. It's up to you as the user to decide what that is. And even to the point that you can take the OpenVX runtime and you can split it and have part of it run on the host, have part of it run on the vision CPU, or you can have it run on, the host, maybe on a GPU and on the vision CPU. It's up to you. And it sounds, it's easy for a programmer then to use the vision processor in the application environment that you need for your application. And that's the point of giving so much control to you on how this integrates with a host processor and the rest of the SoC. All right. So vision, there's no question that the capabilities around vision and having vision in machines is going to change our world, and largely in ways that we haven't even begun to comprehend. We're starting to see the first vestiges of that in cars. It's interesting to read about self-driving cars. I hesitate to say autonomous cars because really the cars that we can get today aren't autonomous, but the lane keeping capabilities and the level of capability that's available today, even though it's very new and young and early, I guess, in the development, is also quite powerful. But if you look at this 10 years from now, in 2026, you can only imagine how much this has taken over a lot of the electronics that we interact with and how much it'll change the world around us and how we interact with the world and how we interact with the digital world around us. In that, the change, the way we use it in 2026 has largely not even been thought of yet. Because as this capability advances, again, 2-3 years ago, this wasn't realistic. We couldn't do this just because the process technology and processor technology wasn't there. This will continue to advance, and this power will become much more powerful over the next few years. This is still very much in its infancy. And when you look at this processor, I've been building processors and architecting processors for the last 35 years. These are extremely high performance machines, combining a lot of different units, bringing together capability, but doing so in a way that keeps the power consumption down, that makes them practical for embedded applications. We will continue to learn about this technology as we move forward and how it's being used and refine it. And in 10 years, it'll be staggering what we can do. And to put that in perspective, 10 years ago, in 2006, the iPhone had not been introduced yet. So you can see how fast the world changes around us. And vision is going to accelerate that change in many ways. And I think in 10 years, we'll take vision for granted. It'll be ubiquitous and largely invisible because we will take it for granted. And in fact, rather than, it sounds a little bit overbearing almost right now, but just like leaving your cell phone behind, if you leave it at home when you come to work, you almost have to turn around and go back and get it. If you don't have vision in whatever it is 10 years from now, it'll be annoying like that. You'll want to go back and find it again. But this is being enabled by processors like this one, the EV6 family, which brings together tremendous levels of integration, tremendous capability with scalar, very high performance scalar RISC, scalar CPU, wide vector DSP capability, and specialized CNN engine. Again, bringing low power consumption, but with very high performance, but also flexibility in terms of programming, delivering much higher performance than previous generations. Of course, part of that's due to the dedicated CNN engine, which is almost essential in this kind of an application, but also because of the vision, the vector DSP and the capability they're bringing support. And of course, these support the full range of vision streams that customers are asking for today. And as I said, I expect that will continue to advance from 4K to 8K and eventually. And so future generations of processor will have much higher capabilities. And of course, we have a full tool set so that the folks that have to do the programming can do that in a way that allows them to control the underlying environment and to not have to get too into the hardware details. All right, Chris, that's the last slide. Let me throw this back to you, and I'm going to step back one slide. Maybe we can take a few questions.
All right. Thank you, Mike, for a great presentation. We're now going to move on to our Q&A session, but just before we begin with today's Q&A, please fill out the feedback form that's opened up on your computer. And if your pop-up blockers have prevented the form from launching on your computer, you can click on the red survey icon at the bottom of your screen. To complete the form, please press the Submit Answer button at the bottom of the page. Thank you in advance for filling out the feedback form. Your participation in this survey allows us to better serve you. We're going to now move on to our question and answer portion of the event. As a reminder, to participate in our Q&A session, just type your question into the text box located to the right of the presentation window, or click on the Q&A icon at the bottom of your screen, and then click the Submit button. So let's get started now with our first question for Mike. Mike, our first question is kind of a long one, so I'm just going to piece it out to you here, and we'll go from there. It says runtime calls kernel directly and no round trip to host. Can you please let us know more details about that, how the runtime will make a kernel call without penalties, for example, the overhead from user space and vice versa?
So I think the question is asking if you split the runtime across the host and the vision processor. In that case, there could be penalties in terms of latency in the runtime, although the runtime could be partitioned in a way that potentially prevents that, where most of the kernel calls would be made from the vision processor. But absolutely, yeah, if you split the runtime across the host and the vision processor, there'll be some implications in terms of efficiency, I guess is the right word, of the processing. And ideally, you'd want to have the full runtime running on the vision processor. But we do recognize there's instances where we have customers that want to do that. And so we make that capability available to our customers to split the runtime across the host and the vision processor. And there may be reasons they want to do that. Maybe they're doing the pre-processing on the host, for example, and then passing that information. They could easily pass that information then into the memory on the vision processor, where it could then be processed by the CNN engine or by the vision CPU, depending on what they're doing. But it really depends on what application or what their application is and how they are using the processor. The point is that we've created the vision processor so that it's flexible enough to be used in your environment, and you can tailor it to meet your needs rather than us forcing you to use it in a certain way.
All right, thank you, Mike. Our next question is, will MetaWare support System C?
No, we have support for System C in some of the modeling capabilities that we have. MetaWare supports C and C++. It's a compiler and debugger and simulator. But we do have support for System C, but not in MetaWare.
All right, Mike, our next question for you. What is an example power profile for 800 megahertz 4-core systems implemented in 28UM?
I think you're asking for power consumption. Probably a little more than a watt. But when you think about it, compared to other solutions, that's relatively low. But also consider that at 800 megahertz with a 4-core system, you can do a tremendously high level of processing. So this 4K image or 4K video stream, which for most applications today is significant overkill. But as I said, over time we'll see it. But that's one of the nice things about the processor, because it is scalable. You can really target it to your specific application. And you don't have to burn a watt if you don't need to burn a watt. You can burn considerably less than that. In fact, 720, 30 frames per second, you can configure it at around 100 milliwatts. So it just depends on your application.
All right, thank you, Mike. Our next one is, what device technology and process are the power numbers from?
Well, any power numbers that, I don't think we had any in this application, but any power numbers that we put out typically today are done in 28 nanometer, in a 28 nanometer process, usually HPM or HPC plus. But the processor itself, of course, it's process independent. So we have customers that are looking at using it at 55 nanometer, which it gets to be, for their application, it makes sense. For most applications, it wouldn't. But the processor has been designed to be used with 28 nanometer technology and more advanced. We have customers looking at 16 FinFET processes and also 10 nanometer today.
All right, thank you, Mike. Our next one for you. Which OS runs DSP Core?
Well, so we don't. So the OpenVX runtime it's a runtime. It's not really an OS, but that's the operating system or the system that we run on the processor itself. We don't run a specific OS on the Vision CPU or the Vector DSP. There's no reason why you couldn't, but typically you wouldn't. It just doesn't make sense because it's a very specialized task. So the OS, if you will, is the OpenVX runtime.
All right, Mike, we'll move on to the next one. We've got quite a few here for you. Can I add Apex instructions to the EV processors?
That's a good question. So the Apex instructions are a capability that exists with the ARC processors that allow the user to add their proprietary hardware to the processor pipeline and add an instruction to execute that hardware, and that hardware can be blocking or non-blocking. It can be whatever you want. It's actually a very efficient interface that's fully registered. And that does exist for the vision processors. So, yeah, you can add your own custom instructions. A lot of people like to call them that. Really, it's adding your own hardware. And that's important because we have a lot of customers that we talk to have a legacy vision hardware that they've used in the past they want to continue to use. And the Apex interface gives them an easy way to attach that to the processor, to the vision processor, and reuse that legacy hardware.
All right, Mike, another one for you here. Can we use EV6X processors used for CNN training farm? And if yes, what is the performance that we can get out of it?
Yeah, the EV6 processor wouldn't be used to do training. The training would be done on a GPU farm or server farm, although it can be done on much less capable systems. It just takes longer. You're done using Caffe or Torch or TensorFlow, one of the newer, which is really pretty new. But it would be done offline, but not with an EV6 processor with, like I said, a bunch of servers or GPU farm.
All right, Mike. And our next one for you here. Is there any comparison with other vision cores like Movidius, Qualcomm HVX, etc.?
Well, yeah. Typically, so there are a number of other vision solutions out there. They do not have a dedicated CNN engine, so that gives us a much higher level of performance, much higher level of efficiency. We also have the up to 4 vision CPU cores, which is not offered by any of the competitive solutions. So you have a level of scalability and a level of performance with performance efficiency available on the EV6 family processors that you don't get with other solutions. Also, we have the full tool support that I mentioned with OpenVX, OpenCV, OpenCLC, and of course the Metaware compiler. It's a very full tool suite that, again, you don't get with most of the other competitive solutions.
All right, Mike, next one for you here. Are the EV family processors configurable?
They are. So first of all, you can configure the number of Vision CPU cores. You can configure whether each Vision CPU core has the scalar unit and the vector DSP or just the scalar unit. There's a lot of configuration options in terms of memory size. the specific configuration of the cores, some of the periphery around it, the shared memory size, for instance, the debug interface. There's limited configuration capabilities in the engine, CNN engine, and then of course the whole Apex interface, which we just discussed.
All right, thank you, Mike. Next one for you here. I've got try and get through two more after this one. Mm-hmm. Why is the CNN engine a separately licensed option?
Oh, interesting. Yeah, I don't think I mentioned that in the talk here. So we have we've actually licensed the EV6X family processor to a number of customers already, and some of our customers in the application they don't need CNN, so they just use the Vision CPU capability and enjoy the efficiency that brings to them. Other customers need the CNN engine, so if you don't need it, you don't have to license it. Is essentially why we did it as a separate feature. Now, from an integration standpoint, the CNN engine integrates natively into the Vision with the Vision CPUs, and they share all the rest of the resources in the processor, and it's one processor when the CNN engine is there, with or without.
All right, thank you, Mike. Next one for you. When I license the EV cores, how are they delivered?
So we have a tool that's called Architect that allows you to fully configure the cores. It's a graphical interface, so it's very easy to configure the core. And then the output from that is synthesizable RTL that's not encrypted. If you want to mess with it, you can, although we don't recommend it. But so we deliver the cores inside of Architect, and it's an RTL form that is made available or put out from the Architect tool.
All right, the next one for you here, and this will be our last question for you as we're running out of time. Do the EV6 family of processors support cache coherency?
Oh. Yeah, they do. And that's actually a good question. We actually support both cache coherency and I/O coherency. So right, cache coherency support. No, let me just touch briefly here, Chris. So cache coherency is supported for the L1 cache on the Vision CPU cores, and that's of course configurable as well as the I/O coherency, so that you can keep the different cores, the information between the cores coherent as you run the processing of the algorithms, whatever the Vision algorithm you're running. All right, Chris, it's all yours. Thank you.
All right. Thank you, Mike, for a great Q&A and a great presentation. That's all the time that we do have for questions for today. Once again, if we didn't get to your question today, someone will get back to you via email. And for more information related to today's webinar, please visit any of the resource links available in the green folder icon at the bottom of your screen. Within the next 24 hours, you will receive a personalized follow-up email with details and a link to today's presentation on demand. Once again, we'd like to thank you for attending today's webinar, Enabling Machines to See with Efficient Embedded Vision Processors, brought to you by Tech Online and Synopsys. This webinar is copyright 2016 by UBM. The presentation materials are owned by our copyright by Tech Online and Synopsys, and the individual speaker is solely responsible for his content and opinions. On behalf of our guests, Synopsys and Mike Thompson, I'm Chris Keats. We'd like to thank you for joining us, and we hope you have a great day.